Hello everyone, my name is Emory Perry and my partner is Sean Krautheim. This project demonstrates the Beer-Lambert Law, more commonly known as Beer's Law. This is the final project for our modern optics class in the physics department at the University of Georgia. The purpose of this project is to demonstrate some optical principle using a 3D printed aperture in a smartphone. We decided to demonstrate the Beer-Lambert Law by comparing different concentrations of T with a 3D printed spectrometer in an iPhone 6s. Spectroscopy is defined as a technique to examine how electromagnetic waves interact with matter. A spectrometer is an apparatus that separates white light into its constituent wavelengths by using a diffraction grating or a similar apparatus. And spectra is the range of colors dispersed from white light. By this means, it is possible to compare wavelengths and their respective intensities. The Beer-Lambert Law states that the absorbance of light of a particular wavelength is directly proportional to the concentration of a solution. When a solution is darker in color, it tends to have a higher concentration and a higher absorbance of light. So generally speaking, a more concentrated solution absorbs a greater amount of light. The law is often expressed as A equals epsilon LC. A is absorbance, epsilon is molar absorptivity, L is the path length difference of the sample, and C is the concentration of the solution. Furthermore, the transmittance, written as T, is the measure of the incident intensity of light before it passes through the solution, I0, over the outcoming intensity, IT, as seen in the second equation. In the third equation, you can see absorbance can be calculated from the transmittance as the negative law of the transmittance. The molar absorptivity, path length difference, and the concentration can be combined and defined as alpha L equals epsilon LC, where alpha is the absorption coefficient and L is the length of the interface through which the light passes. The law can then be reorganized as seen in the last equation. This experiment will use these principles to demonstrate the Beer-Lambert Law by comparing different known concentrations of T to the light that passes into a spectrometer built via 3D printing. Certain wavelengths will be examined to look at how the T absorbs certain types of light at those wavelengths. This experiment employed a MakerBot replicator desktop 3D printer, using a design for the spectrometer from Public Laboratory. The spectrometer is designed to be adhered to a mobile phone, made of 3 individual printed parts, a base and 2 body pieces. The body pieces were glued together to create a permanent bond. A diffracting apparatus was attached to the base before the base was also attached to the body. Other materials required to conduct this experiment include a broad spectrum light source, cuvettes for holding solutions, and the solution itself. You can see in the images the design of the spectrometer and then the actual printed version used in the experiment. In this experiment, the light source was placed on a table using a desk lamp, with the direction of light pointing onto the white sheet to diffuse the light. In experiments where no diffuser was used, the spectrometer had too much light inside the body and images were washed out. Solutions were prepared from one strong batch of T steeped with distilled water. Using distilled water eliminated impurities from tap water which may influence absorption. To then obtain the various solutions, the T was diluted with additional distilled water by a certain percentage. This eliminated differences that could have occurred in the brewing process. The cuvette with the particular experimental solution of T was attached with putty directly in front of the opening in the spectrometer, allowing the light to pass through and only through the cuvette into the spectrometer. This can all be seen in the first diagram. Once this was set up, an image of the spectra was captured on an iPhone 6s. This image was then uploaded to Spectral Workbench where it could be analyzed using software on the site. This was done for each concentration of T. The concentrations chosen were 20, 40, 60, 80, and 100%, and a control solution of 0 concentration, purely distilled water. The 6 solutions can be seen in the bottom right image. Several wavelengths were chosen for examination based on finding wavelengths where spectra were defined, finding where reductions in intensity were most clearly defined, and avoiding wavelengths which exhibited recording problems such as overexposure. The chosen wavelengths were 437 nanometers violet, 490 nanometers cyan, 535 nanometers lower green, 557 nanometers upper green, and 590 nanometers orange. The red band was avoided due to high levels of overexposure. Plots were created to compare concentration versus relative intensity, and a linear regression was run where the slope represents the total drop in intensity across the experiments, and the intercept is the initial incident value. Standard error of these datasets was also calculated and are the assumed uncertainties. R and R squared values were collected as well at this point to assess the goodness of fit. We used the equation listed on the screen to model the absorbance that was discussed in the background. Looking at images of spectra that were gathered alone, there seems to be 3 very easily discernible patterns. Without a doubt, as concentration increases, violet light gets absorbed dramatically fast. The cyan band additionally seems to follow this pattern, but remains visible much longer than the violet band. Lastly, there also seems to be a general reduction in light intensity across the entire spectrum. The numbers gathered seem to support this. Light at the 437 nanometer wavelength displayed a very high absorbance. There is a high uncertainty, but since the violet light was unclear, this was expected. Middle range wavelengths displayed a much better fit with lower uncertainties. It is interesting that the lowest absorption is at 557 nanometers. By comparing the wavelengths, it is seen that the warmer colors have low absorptions while the cooler colors have high absorptions. All of these values discussed seem to display a strong correlation with their models based on their R-squared values. These values tend to decrease as wavelengths increase, which seems to match the data's tendency to become more unpredictable at longer wavelengths. The graph in the top left corner shows the concentration plotted against the relative intensity for each chosen wavelength fit to the linear model, while the graph on the bottom shows the spectrum set with the wavelengths marked where measurements were taken. The results gathered by this experiment seem to confirm not only the Beer-Lambert law, but our general understanding of how light and color work. There is not a particularly high margin of precision in this experiment. Washout was a large problem due to the quality of the camera, but this could be improved with a higher quality camera. Light pollution in the spectrometer was another concern. Due to the construction of the device, light may have entered the spectrometer that did not pass through the cuvette. It is certainly possible to improve on this experiment's design. With a higher cost of production, there would be a higher level of accuracy. Regardless, this experiment still serves as strong proof of Beer's law in spectroscopic techniques. Thank you.